Hello, welcome back. Let's look at a few more examples of asymptotic notation, especially big O notation. Consider the following: log n to the base a and log n to the base b. Okay, so I'm going to show the following: log n to the base a is equal to log n to the base b. Right? How do I do that? Okay, what I'm going to do is that I'm going to use change of base here. Okay, I'm going to write log n to the base a in terms of log n to the base b, and here's how I will write. Is this correct? Let me just see. Okay, so this is a change of base, and this is right. This is my c, constant c. Okay, so I know that there is a constant, so there exists. So I know there is a constant c, such that log n to the base a is equal to c times log n to the base b, and therefore this is true. And in fact, I didn't assume anything about a and b, right? As long as this exists, 1 by log a to the base b, this is fine. So, so therefore, this side is also true. And if I know both sides, f of n is equal to O of g of n and g of n is equal to f of O of n, what do I know? I know the following: this is equal to theta. So this means that these two functions are asymptotically similar, same. That's what theta means. Okay, right. So therefore, what I mean, so that's why whenever people talk about asymptotic complexity which involves log factor, they don't talk about the base, right? Because the base of the log does not affect. You know that you can change it to any the factor you want, and asymptotically they are the same. So that's therefore we are going to always assume log is to the base 2. That's how most times we will assume. In most if you are reading any books, etc., in computer science, wherever they have used log, it's going to be assumed as it is to the base 2 if it's not mentioned, right? Okay, let's now look at another example. So we are going to go through a few more examples to kind of basically go through the most common functions which are there. What about n square and 2 raised to n? Which is bigger? Okay. We guess this, right? So we guess this. We guess this is true, right? So what if I have to prove this? What is it I have to do? I have to take the. I have to show. I have to give. To give. I have to give constant c n0 such that so I'm going to take and n0, we will come to it. Okay, right now I don't know what I'll be taking. So let's have, so since c is equal to 1, this is what I need to prove, right? This is to prove, and this can be seen because just take log on both sides and this becomes log. This is true for all n greater than or equal to 4. This is going to be true. You take 4, this becomes 4, and this side also is 4. So, okay, so this implies this fact. We know this fact, and therefore this implies this fact. And therefore n square is equal to big O of 2 raised to n. Okay, here's another example. What about this n and 2 raised to root n? Here's what I do. I'm going to substitute n by n square by m. So what is here? This is m square, and this is 2 raised to root n becomes 2 raised to m. Right? This we know is true from here. Okay. So this is, therefore this becomes. Okay, now you can see that this is also true, right? I could have taken this n raised to 10 in place of n square, and then this would have become n raised to 10, and this would have been 10, and I should have taken n to be something like 6, like not 6, 2 raised to 6. 2 raised to 6 comes is 64, so this n becomes 64, and log n is 6, and this is 60 is less than or equal to 64. That's also fine, right? So this is also good, this is also good. Now what about this? Log n square, log n the whole square, and n. Again, there's a substitution hidden here. To substitute log n by m. So this becomes m square, and this becomes 2 raised to m. We know this, right? We know this fact. Okay. So again, this becomes right. Is it clear? Okay. Now, what else is there? Here is something else. Here's something else. Claim n factorial is equal to order of n raised to n. This is a little more tricky, and I'm going to prove this by proof. For this, I'm going to take c is equal to 1. Okay, n0 or something I'll fix a little after let's go through it and see how to fix it. So therefore I have to prove the following, right? N factorial is less than or equal to n raised to n. When is this true? Actually, if I take 2, 2 factorial is 2, 2 raised to 2 is 4, that's fine. So I could have even taken n0 is equal to 1. Okay, so this is fine. So I'm going to prove n factorial is less than or equal to n raised to n for all n greater than or equal to 0. Right. And how is the proof? The proof is the following. Proof by induction. So the proof is by induction and on n, and the base case is n is equal to 1, and we know this is correct, right? Okay. Now inductive step is the following. Inductive step, I'm going to assume this to be true. So assume this claim is assumed to be true for all n less than or equal to k. And then I'm going to prove the claim for k plus 1. Right. So let's take k plus 1 and see. So what is it? This is k plus 1 factorial. Right. So that is equal to k factorial into k plus 1. Right. Okay. Now what is k factorial? I know a relation by k factorial. I know this fact is true because from my assumption, right? From my inductive assumption, I know this fact that k factorial is less than or equal to k raised to k, and therefore I can write this as k raised to k into k plus 1. Right. Here comes another thing, and this I can write as the following. This is less than or equal to k plus 1 raised to k, because this k could have been k plus 1. Sorry, this k plus 1 is greater than this k, and therefore k raised to k is less than or equal to k plus 1 raised to k, right? And therefore this is less than or equal to k plus 1 raised to k plus 1, and k, and I'm done because I've proved k plus 1 factorial is less than or equal to k plus 1 raised to k plus 1, and that's exactly what we had done, right? This is a proof by induction. So what we are basically going through is we are going to go through a lot of examples. We are seeing a lot of examples for you to get familiarized with how functions grow in an asymptotic sense, right? So this is clear. Okay, what we are going to do next is the following. I'm going to give you a list of functions, and we are going to order them according to the rate of growth of these functions, right? Let me just list down log n, log of log n, right? Now n raised to 10, n cube plus 2n. So okay, n log n and log n square. What is 2 raised to n, 2 raised to 2n, right? 2 raised to root n. Okay. Now let's see. N times 2 raised to n. Okay. So n plus log n. Right. Now I'm going to list them according to the order in which, according to its rate of growth. Let me also have n factorial, n raised to n. Right. Kind of we have seen kind of all the different kinds of functions, right? And if I want to order them, this is how it's going to be. Okay, if you are not able to see why a certain relation is not true, you need to go back and work it out. We have gone through so we have seen so many examples that the proofs of all these things are hidden here. Okay, it's something we would have already seen. So let me see. So I'm going to write, so log of log n is going to be less than or equal to log n. So when I write less than or equal to, it means log of log n is equal to big O of log n. Okay. And what is the next thing which can happen? The next thing is, so n log n is there, right? Nothing to do with n, right? So this is going to be, n plus log n is there. So this is n plus log n. So we are done with this. Next is n log n. Okay. The next is, we missed log n square there. So this is log n square. And then it is n plus log n. Okay, and then n log n comes in. Then we have n cube and n raised to 10. So this is going to be less than or equal to n cube plus 2n less than or equal to n raised to 10. Then we have all these raised to functions. Which is going to be the smallest? 2 raised to root n. Okay, then among these. Which is better? This is or this? Okay, so this is. Okay, now this is a question. Is this or this bigger? So what is 2 raised to 2n? That is 2 raised to n, the whole square, right? And this is n into 2 raised to n. Okay, so this is 2 raised to n into 2 raised to n. This is n into 2 raised to n. What is it you are going to see? This has to be bigger, right? So this therefore n into 2 raised to n is less than or equal to 2 raised to n square, or 2 raised to 2n. So this 10, this 10, this 10, this 10. Next what? These things, right? So n factorial is going to be greater than this 2 raised to n. This is our order. So what we have seen here is the following, right? So for example, what I want to say is that, see, if n square, see if something like n square plus any constant, let's say 10, this is the same as O of n square, right? So constants kind of disappear, right? Constant addition kind of disappear. What about constant multiplication? This is also same as O of n square, right? So any function, this is true. F of n plus some constant c means this is same as f of n, right? In fact, this could have been any function g of n which is less than or equal to f of n. So you take any function here which is less than or equal to f of n, this could have been true. Okay, so I could have put a constant here also, 100. If there is a constant here, 100 would have been here. Okay. Right, so multiplication by constants it disappears in the order notation. Addition by constants disappear. So addition by any small functions disappear. What about multiplication by an n? So multiplication by n kind of raise this thing. Okay, this becomes n cube.